Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 6, Algebra of Points and One-Dimensional Coordinate Systems. Section 54, the analytic expression for a projectivity in a one-dimensional primitive form. Let a scale be established on a line L by choosing three arbitrary points for P0, P1, P infinity, and let the resulting field of points on a line be made isomorphic with a field of numbers 0, 1, a, ... so that P0 corresponds to 0, P1 to 1, and in general PA to A. For the exceptional point P infinity, let us introduce a special symbol infinity with exceptional properties, which will be assigned to it as the need arises. It should be noted here, however, that this new symbol infinity does not represent a number of a field as defined on page 149. We may now derive the analytic relation between the coordinates of the points on L, which expresses a projective correspondence between these points. Let x be the coordinate of any point of L. We have seen that if the point whose coordinate is x is made to correspond to either of the points, 1, x prime equal to x plus a, where a is not equal to infinity, or 2, x prime is equal to a times x, where a is not equal to 0. Where a is the coordinate of any given point on L, each of the resulting correspondences is projective, Theorem 2 and Theorem 4. It is readily seen, moreover, that if x is made to correspond to 3, x prime equal to 1 divided by x, the resulting correspondence is likewise projective, for we clearly have the following construction for the point 1 divided by x, figure 77. With the same notation as before for the construction of the product of two numbers, let the line xa meet L infinity in x. If y is determined as the intersection of 1x with L0, the line by determines on L a point x prime such that xx prime is equal to 1 by definition. We now have the pencil x is perspective with center A to the pencil x, is perspective with center 1 to the pencil y, is perspective with center B to the pencil x prime. The three projectivities, 1, 2, and 3, are of fundamental importance, as the next theorem will show. It is therefore desirable to consider their properties briefly. We will thus be led to define the behavior of the exceptional symbol infinity with respect to the operations of addition, subtraction, multiplication, and division. The projectivity x prime equal to x plus a from its definition leaves the point P infinity, which we associated with infinity, invariant. We therefore place infinity plus a equal to infinity for all values of a, where a is not equal to infinity. This projectivity, moreover, can have no other invariant point unless it leaves every point invariant. For the equation x equal to x plus a gives at once a equals 0, if x is not equal to infinity. Further, by properly choosing a, any point x can be made to correspond to any point x prime. But when one such pair of homologous points is assigned in addition to the double point infinity, the projectivity is completely determined. The resultant or product of any two projectivities, x prime equal to x plus a and x prime equal to x plus b, is clearly x prime equal to x plus the quantity a plus b. Two such projectivities are therefore commutative. The projectivity x prime equal to ax, from its definition, leaves the points 0 and infinity invariant, and by the fundamental theorem, Theorem 17 of Chapter 4, cannot leave any other point invariant without reducing to the identical projectivity. As another property of the symbol infinity, we have, therefore, infinity equal to a times infinity, where a is not equal to 0. Here, also, by properly choosing a, any point x can be made to correspond to any point x prime, but then the projectivity is completely determined. The fundamental theorem in this case shows, moreover, that any projectivity with the double points 0, infinity can be represented by this equation. The product of two projectivities, a prime equal to ax and x prime equal to bx, is clearly x prime equal the quantity ab times x, so that any two projectivities of this type are also commutative. Theorem 6. Finally, the projectivity x prime equal to 1 divided by x, by its definition, makes the point infinity correspond to 0 and the point 0 to infinity. We are therefore led to assign to the symbol infinity the following further properties. 1 divided by infinity is equal to 0, and 1 divided by 0 is equal to infinity. This projectivity leaves 1 and negative 1, defined as 0 minus 1, invariant. Moreover, it is an involution, because the resultant of two applications of this projectivity is clearly the identity. i.e., if the projectivity is denoted by pi, it satisfies the equation pi squared equal to 1. Theorem 11. Any projectivity on a line is the product of projectivities of the three types 1, 2, and 3, and may be expressed in the form 1. X prime is equal to ax plus b divided by the quantity cx plus d. Conversely, every equation of this form represents a projectivity if AD minus BC is not equal to 0. Assumptions A, E, and P. Proof. We will prove the latter part of the theorem first. If we suppose that C is not equal to 0, we may write the equation of the given transformation in the form, equation 2, x prime is equal to A divided by C plus the quantity B minus AD divided by C divided by the quantity Cx plus D. This shows first that the determinant AD minus BC must be different from 0. Otherwise, the second term on the right of equation 2 would vanish, which would make every x correspond to the same point, A divided by C, while a projectivity is a one-to-one correspondence. Equation 1, moreover, shows at once that the correspondence established by it is the resultant of the 5, x1 is equal to c times x, x2 is equal to x1 plus d, x3 is equal to 1 divided by x2, x4 is equal to the quantity b minus ad divided by c times x3, x prime is equal to x4 plus a divided by c. If c is equal to 0 and ad not equal to 0, this argument is readily modified to show that the transformation of the theorem is the resultant of projectivities of the types 1 and 2. Since the resultant of any series of projectivities is a projectivity, this proves the last part of the theorem. It remains to show that every projectivity can indeed be represented by an equation x prime equal to the quantity ax plus b divided by the quantity cx plus d. To do this simply, it is desirable to determine, first, what point is made to correspond to the point infinity by this projectivity. If we follow the course of this point through the 5 projectivities into which we have just resolved this transformation, it is seen that the first 2 leave it invariant, the third transforms it into 0, the fourth leaves 0 invariant, and the fifth transforms it into a divided by c. The point infinity is then transformed by equation 1 into the point a divided by c. This leads us to attribute a further property to the symbol infinity, namely, the quantity ax plus b divided by the quantity cx plus d is equal to a divided by c when x is equal to infinity. According to the fundamental theorem, Theorem 17 of Chapter 4, a projectivity is completely determined when any 3 pairs of homologous points are assigned. Suppose that in a given projectivity, the points 0, 1, infinity are transformed into the points p, q, r respectively. Then the transformation x prime equal to r times the quantity q minus p times x plus p times the quantity r minus q, all divided by the quantity q minus p times x plus the quantity r minus q. Clearly transforms 0 into p, 1 into q, and by virtue of the relation just developed for infinity, it also transforms infinity into r. It is, moreover, of the form equation 1. The determinant AD minus BC in this case is the quantity q minus p times the quantity r minus q times the quantity r minus p, which is clearly different from 0 if p, q, r are all distinct. This transformation is therefore the given projectivity. Corollary 1. The projectivity x prime equal to a divided by x, a not equal to 0 or infinity, transforms 0 into infinity and infinity into 0. Assumptions A, E, and P. For it is the resultant of the two projectivities, x1 equal to 1 divided by x, and x prime equal to a times x1, of which the first interchanges 0 and infinity, while the second leaves them both invariant. We are therefore led to define the symbols a divided by 0 and a divided by infinity as equal to infinity and 0 respectively, when a is neither 0 nor infinity. Corollary 2. Any projectivity leaving the point infinity invariant may be expressed in the form x prime equal to ax plus b. Assumptions A, E, and P. Corollary 3. Any projectivity may be expressed analytically by the bilinear equation cxx prime plus dx prime minus ax minus b is equal to 0. And conversely, any bilinear equation defines a projective correspondence between its two variables, provided AD minus BC is not equal to 0. Assumptions A, E, and P. Corollary 4. If a projectivity leaves any points invariant, the coordinates of these double points satisfy the quadratic equation cx squared plus the quantity d minus a times x minus b is equal to 0. Assumptions A, E, and P. Definition: a system of n numbers arranged in a rectangular array of m rows and n columns is called a matrix. If m is equal to n, it is called a square matrix of order n. Footnote: for a development of the principal properties of matrices, chiefly Bocher, Introduction to Higher Algebra, pages 20 forward. The coefficients a, b, c, d of the projective transformation equation 1 form a square matrix of the second order, which may be conveniently used to denote the transformation. Two matrices, A, B, C, D, and A', B', C', D' represent the same transformation, if and only if A is to A' is equal to B is to B' equal C is to C' equal D is to D'. The product of two projectivities, x prime equal to pi of x equal to the quantity ax plus b divided by the quantity cx plus d, and x double prime equal to pi sub 1 of x prime equal to the quantity a prime x prime plus b prime divided by the quantity c prime x prime plus d prime is given by the equation x double prime is equal to pi sub 1 pi of x equal to the quantity a prime plus c b prime times x plus b a prime plus d b prime, all divided by the quantity ac prime plus c d prime x plus b c prime plus d d prime. This leads at once to the rule for multiplication of matrices, which is similar to that for determinants. Definition: the product of two matrices is defined by the equation a prime b prime c prime d prime times a b c d is equal to a prime plus c b prime, b a prime plus d b prime, ac prime plus c d prime, bc prime plus d d prime. This gives, in connection with the result just derived, Theorem 12, the product of two projectivities, pi equal to the matrix A, B, C, D, and pi 1 equal to the matrix A prime, B prime, C prime, D prime, is represented by the product of their matrices in symbols pi 1 pi equal to the matrix A prime, B prime, C prime, D prime times the matrix A, B, C, D, assumptions A, E, and P. Corollary 1. The determinant of the product of two projectivities is equal to the product of their determinants. Assumptions A, E, and P. Corollary 2. The inverse of the projectivity pi equal the matrix A, B, C, D is given by pi inverse equal to the matrix D minus B minus C A is equal to the matrix A, C, B, D, where A, B, C, D are the cofactors of A, B, C, D, respectively, in the determinant A, B, C, D. Assumptions A, E, and P. This follows at once from Corollary 3 of the last theorem by interchanging x and x prime. We may also verify the relation by forming the product pi inverse pi equal to the matrix AD minus BC 0, 0, AD minus BC, which transformation is equivalent to the matrix 1, 0, 0, 1. The latter is called the identical matrix. Corollary 3. Any involution is represented by the matrix A, B, C minus A, and that is by x prime equal to the quantity ax plus b divided by the quantity cx minus a, with the condition that a squared plus bc is not equal to 0. Assumptions A, E, and P.
Projective Geometry, Volume 1. This book was written by Owald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.